Hi guys again. So let's solve two more questions to see the application of most powerful test. Let's do a simple example that we use a lot. Let's say we have a random variable x where x is distributed as exponential with parameter theta. Okay, and the parameter space of theta is, all positive real numbers. So let's say we want to test that theta equal theta 0 versus theta equals theta 1, and let's say that theta 0 is let's say less than theta 1. Okay, so this is given to us. Then find the most powerful test of size alpha. Let's say this is part A. Okay, let's define that. So, and let's say we assume that we have a random sample of size n. Okay, then what we have to do is find the likelihood function. So likelihood function for exponential is 1 over theta to the n e to the minus summation xi over theta, where theta is greater than 0 and each xi greater than 0. Okay, then find the simple likelihood ratio. So this is the first step, the simple likelihood ratio, L, which is L theta 0 over L theta 1. So replace theta by theta 0 and theta by theta 1, and then get the ratio. So 1 theta 0 to the n minus summation xi over theta 0, and 1 over theta 1 to the n e to the minus summation xi over theta 1. So we have theta 1, theta 0 to the n e to the minus summation xi 1 over theta 0 minus 1 over theta 1. So this is our simple likelihood ratio. So what is our most powerful test? Is reject A0 if L is less than or equal to K. Don't forget to write the equality sign here. Okay, so what is our L? Is theta 1 over theta 0 to the n e to the minus summation xi 1 over theta 0 minus 1 over theta 1 less than or equal to K. So our statistic here is summation xi. As you can see, there's no other x term. So e to the minus summation xi. So theta 1 minus theta 0 times theta 1 less than or equal to theta 0 over theta 1 to the n. K. Take the natural logarithm of both sides. Then we have summation xi theta 1 minus theta 0, theta 1 less than or equal to ln theta 0, theta 1 to the a, k. So here, okay, so now we have to look at the condition on the theta 0 and theta 1. Here we assume that theta 1 is greater than theta 0. So we have one minus sign here. So this part is minus theta 1 plus theta 0. Since we assume that theta 1 is greater than theta 0, so this is negative. Then if you write the rejection rule on just summation xi, so what we have to do is get this part, theta 0, theta 1 times ln theta 0 over theta 1 to the n times k divided by theta 0 minus theta 1. Okay, so since this is negative, we change the direction. So let's say this is our C. So our rejection rule is reject A0 if summation xi greater than or equal to some unknown value c. So now we have to find this c. How we are using c? We are using the given information. So what we know is alpha. Alpha is given to us. At the beginning we pre-specified that. And what is that? It is the probability of reject H0. What is our reject H0 condition? Summation xi greater than or equal to c. Okay, so this is the rejection rule on null hypothesis. Given that null hypothesis is correct, then theta equal theta 0. So under this condition, we can find c. So what we need here is the PDF of summation xi. So we need to find this. Okay, and if we can relate this with distribution with some statistical table, then we have to do that. As you can see, we start with exponential. Summation of xi will be gamma. Then it is very related with the chi-square distribution. So try to change the distribution gamma to chi-square by multiplying with some constants. Okay, so when x distributed as exponential theta, we know that summation xi for a random sample distributed as gamma. So we are summing n of them and theta. So you know we can change summation xi to a chi-square random variable by just changing the scale parameter here. If you multiply whole random variable with 2 and divide by theta, we will obtain a gamma distribution where the scale parameter is 2, which is a chi-square distribution. So multiply summation xi by 2, divide by theta. Okay, now we have gamma and 2, and which is same as chi-square with 2 and degrees of freedom. Okay, so keep this here. Okay, and then use alpha again, probability that. Okay, so multiply both sides by 2 and divide by theta 0, because our theta now equals to theta 0. It's given in the condition. So 2 times summation xi over theta 0. Do the same thing to the other side of the inequality. So 2 times c over theta 0, where theta equals to theta 0. So under this condition, 2 times summation xi over theta 0 distributed as chi-square with 2 and degrees of freedom. This part is 2c theta 0. And we know that this probability is alpha. Alpha is like, again, a small number, 0.05 or something like that. So if we draw the shape of the distribution here, so let's say this is a PDF of chi-square with 2 and degrees of freedom, then we want that this chi-square random variable greater than or equal to 2c over theta 0, so upper bound, equals to some small alpha value. Okay, so this part is 2c over theta 0. We know that alpha is small, and for chi-square distribution, this point is a chi-square with 2 and degrees of freedom, where the upper tail probability is alpha. Okay, then now we can easily define the value of c. Then our unknown c will be theta 0 chi-square 2n alpha over 2. So now our most powerful test of size alpha will be rejecting A0 if summation xi, okay, so what was the direction here, greater than or equal to c. Our c is this one, chi-square 2n alpha over 2. Okay, so this will be our most powerful test of size alpha. Okay, so this is the end. And let's say here we want to find the type 2 error probability. Okay, so find beta. Okay, so what is beta? As probability that not reject H0 given that theta equals to theta 1. Okay, so the alternative hypothesis is true case. So we know the reject A0 rule. Okay, so write this in terms of 1 minus reject A0 when theta equals theta 1. Okay, so 1 minus probability that summation xi. Now replace our c by the quantity that we already found. Okay, so theta 0 chi square 2n alpha over 2 given theta equal theta 1 in this case. Okay, so now again change this to a chi-square random variable because now our theta is actually theta 1, not theta 0 anymore. So theta 0 is just another number for us at this point. So 2 times summation xi over through theta 1, 2 times theta 0 chi square 2n alpha theta 1. Okay, given theta equals theta 1. So now this is a chi-square random variable with 2n degrees of freedom. So 1 minus probability that chi-square with 2n degrees of freedom greater than or equal to. So these two cancels out. So we have theta 0 over theta 1 chi-square 2n alpha. So this will be the power. Okay, so from the hypothesis we already know the values theta 0 and theta 1, and then when we know the sample size and alpha is given, so we can easily calculate this probability. Okay, so let's solve another question. So let's say in this question we assume that we have just one single random variable. Okay, so on the basis of a random sample of size 1 only. Okay, from the PDF f of x theta equals theta x to the theta minus 1, where the range of x is between 0 and 1 and theta greater than 1. Okay, so the hypothesis is given as theta equals theta 0 and alternative given as theta equals theta 1. Okay, so let's decide our value on the theta 0 and theta 1. Okay, so here we assume that this time, let's say, theta 0 is greater than theta 1. So this is given to us, so we already know the values. And then find the most powerful test of size alpha. Okay, so we don't have a random sample of size n, so we have just one single random variable. So our simple likelihood ratio is just the, actually this is the likelihood function ratio of these two, but these are actually equals to the PDF points when theta equals theta 0 over the PDF and theta replaced by theta 1. So do that here. So we have theta 0 x to the theta 0 minus 1 over theta 1 x to the theta 1 minus 1. Okay, so then our ratio will be theta 0 over theta 1 and x to the theta 0 minus theta 1. So this will be our simple likelihood ratio. Okay, so our simple likelihood ratio. So what is our most powerful test? Will be reject H0 if L less than or equal to K. This is our rule. We already derived this procedure, where we get this. Okay, so we obtain our L as this one. So theta 0 over theta 1 x to the theta 0 minus 1 less than or equal to K. So x to the theta 0 minus theta 1 less than or equal to theta 1 over theta 0. Okay, so take the take the ln of both sides here. Maybe we don't need to do that, but let's do it ln x, and then ln of theta 1 theta 0 to the k. So now use the condition. It is given in the hypothesis part theta 0 is greater than theta 1, so this quantity is positive. Then we don't have to change the direction. Okay, so it will be like that. So we have ln theta 1 theta 0 to the k divide by theta 0 minus theta 1. Okay, so since everything is based on x, here you don't have to use the ln transformation. Okay, so try to write this in terms of x. So how we can do that? Again, take the exponent. Okay, then x, you know, it's a monotone increasing function, so we don't have to get the quantity. So we have e to the ln, we don't have to change the direction, over theta 0 minus theta 1. So this will be our c part. Actually, you don't have to write the whole thing. Okay, so what is our rejection rule? So reject a0 if x less than or equal to c. So here basically we define the direction of our test. Now our job is to find the value of c using the distribution of x, because we only have one random variable. Okay, again, finding the c part is always done by the given information, which is alpha. So we already know the value of alpha. Okay, so then probability of reject a0, which is this condition under the fact that theta equals to theta 0. Okay, so we have the PDF. So this is the CDF formula where x is replaced by c and our true theta value is theta 0. So here what we have to do, okay, so lower bound of x is 0 till value c in the integral. So our true theta value is theta 0 dx. Okay, and this quantity equals to alpha. Okay, finding this, we have x to the theta 0, 0 to c equals to, so c to the theta 0. So this equals to alpha. So then what is the value of c? Is alpha to the 1 over theta 0, or theta 0 to the alpha. Okay. Then what is our most powerful test? We found the value of c. Then we can define the most powerful test of size alpha will be rejecting a0 if our x is greater than, oh sorry, not greater than, less than, write it here, x less than or equal to, okay, so we define it like that, sorry, alpha to the theta 0. Okay, so this is our test. Okay, so this will be the result. So alpha is given, theta 0 is given, so this will be the upper bound if when we have a single random point, sample point, then if x is less than this quantity, we will reject the null hypothesis, otherwise we cannot reject the null hypothesis. If you want to find the power, okay, so this is the end of the question, but let's say we want to find the power. Okay, so power of the test. So it is the power under the case that, sorry, not beta, theta equals to theta 1 case. So probability of rejecting null hypothesis. Our rejection rule is this one. Given that theta equals to theta 1. Okay, so in the CDF formula, we will calculate the case that the lower bound of x is 0. Upper bound will be the quantity that we already found for c. Then write the actual form of the PDF. Here we assume that our true theta equals to theta 1, x to the theta 1 minus 1 dx. Okay, so we have x to the theta 1, 0, alpha, theta 0. Okay, so replacing the quantity here, we will have So we will have alpha to the theta 1 over theta 0. Okay, so this will be the power of the test. So for a given alpha value, theta 1 and theta 0 value, we can numerically define the power of our test. Okay. Another question might be finding the p-value. So finding the p-value is very independent than the finding the c. Only thing that we have to know here is the direction of the test. Okay, so if you want the p-value, so this is the observed significance level. So what we observe, our sample supports the null hypothesis or not. If the probability of the rejecting H0 is very small under the condition that theta equals theta 0, then we will reject the null hypothesis. Otherwise, we cannot reject the null hypothesis. So here we are using just the direction here. Okay, so our statistic here is x. Okay, so we are using which statistics that we observe and the direction of the test, but we are not using the c, we are using the observed value of the statistic. So our statistic here is just x because we have only one sample. Okay, so we have x less than or equal to. So at this point we don't need to find the value of c, so only we are using the observed value from the sample under the condition that theta equals to theta 0. Okay, so here we don't need to find the value of c to be able to find the p-value. Okay, so we are using the observed value. So our statistic here is x less than or equal to, use the direction and then replace it with the sample version under the condition that null hypothesis is true. So this is just a CDF in this case, from 0 to x theta 0, x to the theta 0 minus 1 dx. Okay, and then x to the theta 0. Okay, so from the sample we will get the value of x, theta 0 already given in the null hypothesis, so this will be the p-value. So when you calculate the numerical value of theta 0, if this value is less than alpha, then we will reject the null hypothesis. Otherwise we cannot reject the null hypothesis. Okay, this is how we define the p-value. So it is the observed significance level. Okay, then you will have some more solved questions in the recitation pages. So when you have any questions, we will arrange some Zoom meeting, so you can ask any questions that you want if you don't understand some parts of the solution here, or if you have any other question, so we can meet. I will send you the time and the date of our Zoom meeting. Okay, see you on the next class.